Electron preferences. Now, electrons most prefer a filled shell. A filled shell is going to be, for example, where the second shell is completely filled. So the 2s and 2p, these are going to be completely filled. That makes them very, very happy. Then a filled subshell. Okay, for example, if the 2s is completely full. And finally, the third preference that they have is a half-filled subshell. So for example, if you have the 2p, it would prefer it being half-filled. So electrons, or I should say atoms, are going to really want a filled shell first. If that can't happen, then they're going to want a filled subshell. And finally, if that can't happen, then they want a half-filled subshell. Let's look at a couple examples. Let's say I'm going to look at oxygen. I'm going to write the noble gas configuration because oxygen is noble gas configuration is a lot easier. What is the noble gas before oxygen? Helium. Okay, and then I move forward. So I have the 2s and as well as the 2p. And I'm going to fill in my number of electrons. 2s is completely full. And then the 2p, I am going to have 4 electrons in there. So starting on top, and then I fill them with the rest. This one, oxygen does not like. So it says, seriously, this is my happy face. Yeah, so oxygen does not enjoy this electron configuration. Let's say I'm going to look at nitrogen now. The noble gas before nitrogen is going to be helium. Again, we're working in the second shell, so it's going to be 2s and 2p. The 2s is completely full. The 2p is half full. So it's fairly happy. It's not amazingly happy, but we have a half-filled subshell. Then, if I'm going to look at neon, the noble gas before neon is helium. We have 2s, that's full, and the 2p, that's going to be completely full too. So that is insanely happy. So here we have a filled subshell. I should also note for oxygen is kind of, it's okay, but it does have a filled subshell right here. But even then, it's not that great because really what they're looking at is this last one. So we said electrons most prefer a filled shell, and then they prefer a filled subshell, and finally a half-filled subshell. Let's look at these transition metals. What we notice is something weird happens. Let's look at scandium. Okay, so scandium, we have the 4s is completely full, and then we have 1 electron in the 3d. Okay, that looks normal. So we have 1 unpaired electron. For titanium, the 4s is full. The 3d, we have 2. Vanadium looks normal. We have 2 electrons in the 4s, 3 electrons in the d. But here at chromium, chromium has something weird going on. Notice that the electron in the 4s moves and goes in place of the 3d. The reason why is because now this is a half-filled subshell. So the 3d will steal an electron from the 4s and move it up to the 3d. So now the 3d is super happy. Well, not super happy, but it's fairly happy because it's half filled. Okay, then we have manganese. Manganese looks normal. We have 2 electrons in the 4s, 5 there. So this one's pretty happy too because it's half filled. Okay, then we have iron Notice how now they're starting to double up in the 3D. They're running out of room. Cobalt, nickel. Now look at copper. What happens there? Again, one of those electrons from the 4s gets promoted, in a sense, up to the 3D. Why would it get promoted up to the 3D? Because now you have a full subshell. When it has a full subshell, it is like super, super happy. Extremely, extremely happy. Okay, and then now we have zinc. Zinc is going to be insanely happy because we have a full shell. Not even a full subshell, a full shell. So the thing with this slide is that with transition metals, the transition metals can pull an electron from a lower orbit and pull it up to a higher orbit in order to make the higher orbit happy. Because of the preferences, it is energetically favorable for an atom to gain or lose electrons, and this forms an ion. For example, let's say we're going to look at oxygen. The noble gas before oxygen, or let's write the electron configuration for it. The noble gas before oxygen is helium. We have the 2s as well as the 2p that get filled. The 2s gets completely filled, and the 2p ends up with 4 electrons. So at first they're unpaired, and then they get paired up. Now one way that oxygen could get happy is we could remove one of those electrons. Okay, so if we remove one of those electrons, we'll end up with something like this. Okay, which one is happier? Our oxygen or the one that we removed an electron from? The one that we moved an electron from. So this is going to be fairly happy because it's half full. If we removed one oxygen, is this going to be is oxygen an anion or a cation? If we remove one, oxygen is going to get a positive charge. You're removing a negative from it. Okay, now another thing that it could do is it could gain 2 electrons to get a filled subshell. So let's write the noble gas configuration for that. This electron configuration is insanely happy. Because it's a filled shell. Now oxygen, in this case, is it going to be a cation or an anion? It's going to be an anion because you're gaining a negative charges. And you're gaining an extra 2, so this is going to be a negative 2 charge, or 2 minus. What will oxygen rather do? Would it rather become O positive or O2 negative? It would rather be O2 negative because it has a filled shell. So this is why you see O2 negative and you don't see O positive, because oxygen would rather take the extra time and get 2 electrons so it can get a filled shell. Now here's a question. Why do all alkali metals have similar properties? And why do all halogens have similar properties? what it boils down to is valence shell electrons. Valence electrons, these are the same group, has similar properties because of similar electron configurations in their valence, which means outermost shell. The valence electrons are the electrons in the valence shell. Okay. When we're looking at the valence shell, we are looking at the last shell. So we're not looking at the subshell, we're looking at the shell. So we're looking at, let's say, n equals 1 or n equals 2. All of the orbitals in that last shell. So how many valence electrons do the alkali metals have? Okay, the alkali metals, these are going to be in group 1. In group 1, we said that it has an S1. Therefore, we will have 1 valence electron. How many valence electrons do the halogens have? Okay, halogens are in what group? They're going to be in group 7A. Okay, so you have N, and so that's your shell. It could be 1, 2, whatever. NS2, because you have to fill that subshell, the S subshell, and then you can go to the next block, which would be the P. So N, remember, is just standing for the row number, meaning the shell. And now, because we're in group 7, there's going to be 6 electrons there. If we add them up, not 6, I can't add. There's going to be 5 there. So 5 plus 2, that's going to be a total of 7 electrons. So there are 7 valence electrons for the halogens. The easy way to figure out the number of valence electrons is that the group numbers from 1A through 8A give the number of valence electrons for the elements in each main group. So for example, if you had alkali metals are in group 1, group 1A I should say, so therefore there's 1 electron. For halogens, these are going to be in group 7A, so you can cheat and just say, oh, there's 7 electrons. The number of valence electrons helps determine reactivity / properties, and we've already somewhat talked about this before in previous chapters. An atom wants to get a complete octet. Why do you think they want to get an octet? Because this gives them a full subshell, or a full shell. And an octet basically means 8 electrons in the outermost shell. And as we could see with the oxygen example, atoms will gain or lose electrons to get that octet. Okay, now I want you to label the valence electrons on your own periodic table.